the sheet titled Test Your Capacity. Please come in. So the first set of problems is based on this situation where you have a capacitance, capacity 2C, and it's charged to a potential difference of 2V volts. It's charged to a potential difference of 2V volts, and another capacitor C charged to a potential difference of V volts, right? Now, at time t equal to 0, this switch is activated. At time t equal to 0, this switch is activated. Okay. Once it is activated, we want to know what the current is at time t equal to 0, I at t equal to 0. Then we want to know the potential difference across each capacitor in steady state. And then we want to know the energy loss that takes place, right? Energy loss that takes place by the time the circuit reaches its steady state conditions. These are things that we want to investigate in the problem. Okay. Now, before I activate the switch, the two capacitors are pre-charged. 2C with 2V volts means the charge here is going to be 4CV and the charge here is going to be minus 4CV. Yes or no? The charge on this plate before I activate the switch, that means prior to t equal to 0, would be CV and minus CV. Right? Now, once I activate this switch, that is at time t equal to 0, there would be charge exchange between this plate and this plate, and there would be charge exchange between this plate and this plate. Right? So, at an instant of t, after t equal to 0, suppose by that time this would have lost, see, this plate plus this plate will always be 5. The total charge on this plate plus this plate will always be 5 CV. So, if at a given instant of time, this has charge Q on it, then this would have charge 5 CV minus Q on it. Yes or no? At an instant of time, if this would have charge, this plate would have charge Q on it, then this plate would have charge 5 CV minus Q on it. Right? Yes or no? And if this has charge Q, this would have had charge minus Q. And this then would have, see, this plate plus this plate will always be minus 5 CV. And this would then have minus of 5 CV minus Q at an instant of time t. Q then would be a function of t. Q then would be a function of t. Clear? Yes or no? Now, at that instant of time at t equal to 0, I am going to apply KVL to the loop. I am going to apply KVL to the loop. So, let me go this way. At an instant of time t, I is the current in the loop. I is the current in the loop. So, the drop here is going to be IR. The drop here is going to be IR. The drop here is going to be Q by C. Q by C, charge on the first plate divided by C, is always going to measure the algebraic drop. So, plus Q by C plus Q by C. And then I come down here. The drop from this plate to this plate is going to be charge on the first plate divided by the capacitance. So that means this charge divided by 2C is going to be the drop from this plate to this plate. So then minus 5CV minus Q divided by 2C. This is the algebraic sum of the drops in the loop at an instant of time t. And that's going to be 0. That's going to be 0. Yes or no? Where of course I is dq dt. I is dq dt. Now, at time t equal to 0. So the first part where at time t equal to 0, I want to find the current. How would I do this? Would I need to integrate this to find current as a function of time and then find at put t equal to 0 in that equation? Would I have to do that? Would I have to at all solve the differential equation? Even comparing, do I even have to do that? That's my contention. Say this is the equation. I don't want to solve this equation. At time t equal to 0 without solving the equation. I want to be able to find the current I at time t equal to 0. Very simple. Yes. At time t equal to 0, Q is CV. At time t equal to 0, Q is CV. So if you plug in Q equal to CV, then I would be the current at time t equal to 0. Yes or no? Because at time t equal to 0, Q is CV. Right? So at time t equal to 0, Q is CV. So plug in Q equal to CV and you can solve for I. So IR plus this will become V. Q by C would be V plus this will be minus 4CV divided by 2C equal to 0. Right or no? So this gives me like 2V. So I then turns out to be V by R. At time t equal to 0, as you can see. Right? Second, potential drop in steady state. Now, in steady state, that means that theoretically t equal to infinity, what happens to I? I will become 0. And Q by C would be the drop across this, and 5CV minus Q by 2C will be the drop across this. Yes or no? So at t equal to infinity, I is 0. In this very equation, put I equal to 0, then that would be the steady state. That will give me the steady state charge on the two capacitors. Yes or no? Yes. Right now? No? Okay, I'm saying under steady state what happens? Both the capacitors, they behave like monsters. They offer infinite resistance. And if they offer infinite resistance, the current would be 0 in the circuit, in this loop. So plugging in I equal to 0 means this charge that you get in this equation would be the steady state charge on the capacitor. Yes or no? So at t equal to infinity, I is 0, then Q will be my steady state charge. So let me write Q as QS, means Q steady state by C minus, because this part is 0, minus 5CV minus Q by 2C. That must be 0. Yes or no? I don't have to solve for Q. I just need the value of Q by C, isn't it? So this I could have written as Q steady state. This is also Q steady state divided by C, and this is 2C, equals 5CV minus Q steady state divided by 2C. This will measure the potential difference across one capacitance. This will measure the potential difference across the other capacitance. This would be V steady state across the two capacitors. And how do I find without solving for QSS? Absolutely. Each will be sum of the numerators divided by sum of the denominators. If this is equal to this, then each is sum of the numerators, which is 5CV divided by 2C. 3C. Yes or no? That will be the steady state voltage across the two capacitors. So that's going to be 5V by 3. 5V by 3 would be the steady state potential drop across the two capacitors. Yes or no? Confused kya? Get these ideas right. Don't be misled. Okay? And obviously you realize, there'll be flow of charge from this plate to this plate till these two plates are equalized in potential. There'll be exchange of charge between these two plates till these potentials are equalized. That's when steady state is reached. That means the drop across this will eventually turn out to be the drop across this. And each will be 5V by 3. That's a steady state. Yes. Okay. Under steady state? See, tell me, when would charge exchange between these two stop? when they arrive at the same potential. When would charge exchange between these two plates stop? When they arrive at the same potential. Right? And that is what steady state is all about. When exchange of charge ceases, flow of charge ceases. Right? So the drop, this plate turns out to be equal to this plate in potential. This plate turns out to be equal to this plate in potential. So the drop across this will be measured the same as the drop across this, which is what defines our steady state. Which is what defines our steady state in the circuit. Yes or no? Right? So I know the current at time t equal to 0, which is V by R. Right? This is V by R, and I know the steady state potential drop across, which is 5V by 3. How about it? Right? Now, I need to find the energy loss. Now, that's a fairly simple proposition. Can I wipe this off and compute the energy loss? Yes, change in half CV squared in the circuit. So what is the initial energy of the system? Energy of this is half of 2C into 2V whole square. Right? What's the initial energy of this? Half of C into V squared. That's the initial energy of the system. The final potential energy of the system, hey, in the final state, the drop across both is 5V by 3. The drop across both is 5V by 3. So the total energy in the system would be half of 2C plus C into 5V by 3 whole square. Yes or no? Confused kya? Tell me, where is the problem? Half of 2C into 5V by 3 whole square plus half of C into 5V by 3 whole square. So I take half of 5V by 3 whole square common, and 2C plus C gets added, and all that, the energy loss, which features as heat generated across the resistance, is going to be UI minus UF, loss of energy. Loss of potential energy would be the heat generated in the circuit. What does it turn out to be? Has anyone done the calculation? No. All right. Whatever. So the next bunch of problems based on this situation. Now there are two switches. First, this switch S1 is closed to complete this loop. Capacitor C reaches steady state conditions. Once capacitor C reaches steady state conditions, then switch S1 is disabled and S2 is enabled. And then these two capacitors interact. This loop becomes inactive. There will be exchange of charge between these two capacitors. This then is my charging capacitor. This then would be my charging capacitor. This is getting charged, isn't it? Charge is accumulating on this at the expense of this capacitor. Right? So there are questions based on this. So now, when I activate switch S1, keeping S2 disabled, this will reach steady state conditions. Under steady state conditions, the current in this loop would become 0. And this, no part of epsa will drop across R. This entire epsa will drop across C then. Right? So this will be like C epsa, and this would be like minus C epsa. I hope you understand why this polarity. Okay. So this capacitor then would have reached steady state conditions, preventing further flow of current in this left loop. Do you all understand this? Not an issue? Now at this juncture, this is disabled and this one gets enabled. Right? So now these two capacitors would start to interact with each other. This is an uncharged capacitor, this is a charged capacitor. This plate would exchange charge with this plate would exchange charge with this plate, till such time that the potential of this becomes equal to potential of this becomes equal to potential of this. Yes or no? Now, what are the problems that are based on this? Let's see what is it that they need. Okay, right after I execute S2, what is the current in this loop? That means current through switch S2 right after. That means this is my new time t equal to 0. So at this instant of time, I want to be able to find the current in the loop. I want to be able to find the current in the loop. Clear? Now, say, again, let me get a little general about things. I could just write my equation of current as a function of time, the general differential equation for this loop. So at an instant of time t, say this would have acquired charge q. Obviously at the expense of this, the charge on this would have been c epsilon minus q. This then would have been minus q, and this would have been minus c epsilon minus q. Yes or no? That would be the charge disposition at an instant of time t. And say the current in the loop at that instant of time is I. The current in the loop circulating at that instant of time is I. So now let me apply KVL to the loop. Let me apply KVL to the loop. What's the drop across this? Q by C. KVL at time at t. Q by C is the drop across this. IR is the drop across this. There is an increase here, so minus 2 epsilon increases negative, so minus 2 epsilon. The drop from here to here would be charge on this divided by C. By C. Yes or no? And this must, and then there is a plus epsilon. There is a plus epsilon. All of this must add up to 0. All of this must add up to 0. That's the story. Now what does this give me? This gives me IR, and there is a Q by C plus Q by C, that means 2Q by C. That's equal to epsilon. Epsilon plus epsilon, 2 epsilon. 2 epsilon. Isn't it? Minus epsilon, and there is minus epsilon, so 2 epsilon goes on the right hand side. That's my equation. That's my equation. Okay. At time t equal to 0. So first of all, I want to find I at time t equal to 0. What do I need to solve this equation? No. What would I do? Q equal to 0. At time t equal to 0, Q is 0. Q is 0. Right? And then this would be my current at that instant of time. So I becomes 2 epsilon by R. I then becomes 2 epsilon by R at time t equal to 0. Yes or no? Becomes 2 epsilon by R at time t equal to 0. What's the next part of the problem? Time constant for the charging. This Q is the charge on the charging capacitor. So this I could have written as R dq dt plus Q by C by 2. So this R I can write here. So RC by 2 equals 2 epsilon by R. Yes or no? I could have written this way. And do you realize this quantity then would be my time constant by comparison? This would be my effective R into C. This would be my time constant. Yes or no? This would be my time constant that features here. So time constant for the charging capacitor would be, as you can see, RC by 2. Yes or no? Right? That's first. What's the next part of the problem? Charge would be equal on both the capacitors. Okay, now it might make sense for me to solve for Q as a function of time. Let me just bring down R here. So out of comparison with the standard equation that solves this, right, what would be Q as a function of time? Instead of C, it's like C epsilon into 1 minus e to power minus t by RC. So instead of C, I have C by 2 here. Instead of epsilon, I have 2 epsilon here, isn't it? See, R dq dt plus Q by C equal to epsilon. we've learned how to solve this equation. The solution to this equation was Q equal to C epsilon into 1 minus e to power minus T by RC. Now you don't want to reinvent the wheel. You want to use the same template. The difference between these two equations is, instead of R you have R only, not a problem. Instead of C you have C by 2, and instead of epsilon you have 2 epsilon. Use this very thing. So Q would be, instead of C you have C by 2 here on comparison. So C epsilon by 2. Epsilon ki jagah you have 2 epsilon. Instead of epsilon you have 2 epsilon, right? Instead of epsilon that features here you have 2 epsilon. So Q would be, instead of C, C by 2, instead of epsilon, 2 epsilon. C by 2 into 2 epsilon, right? Yes or no? Into 1 minus e to power minus T by R, and C would be C by 2. Yes or no? That's the solution to the equation. That's the solution to the equation. Q as a function of time. How about it? So this 2 will get cancelled. So C epsilon. So that's Q as a function of time. That's Q as a function of time. Clear? Now, I want to solve for T at an instant. I want to find T, the instant when this charge becomes equal to this charge. That means I'm seeking to look at the instant where C epsilon minus Q turns out to be equal to Q. That's the Q that I'm seeking here in the next part of the problem, right? That's the Q that I'm seeking, yes or no? So that gives me Q equal to C epsilon by 2. Q equal to C epsilon by 2. That means if all that I want to do is, I want to find the instant when Q becomes C epsilon by 2. So let's plug in Q equal to C epsilon by 2 equal to C epsilon into 1 minus e to power minus 2t by RC. I need to solve for T. I need to solve for T. So this C epsilon will get cancelled, and then I have like e to power minus 2t, e to power minus 2t by RC equals half, and I take logarithm of both sides. So minus 2t by RC equals minus log 2, right? So T then becomes RC by 2 log 2. Yes or no? T is RC by 2 log 2. At this instant of time, the charges on the two capacitors will become equal to each other. Yes or no? Confused? So this is the time when the charges will become equal to each other. Yes or no? That's what's the next part of the problem? Okay. Obviously, you know, this is losing energy and this is gaining energy. So we want to find the instant. We want to find the instant when the rate at which energy is dissipated here becomes equal to rate at which energy is consumed there. Yes or no? Now, if you allow me to wipe this off, then I'll address the next part of the problem. Now, see, what's the energy in a capacitor? Q squared by 2C is the energy in a capacitor. Rate at which U changes with time is what? Q by C into dq dt, where dq dt then is the current. Q by C into I, that's the rate at which energy gets dissipated in a capacitor. Q by C into I. Q by C into I, right? Yes or no? Right? So what is it that I want? Say the instant when the rate of change of energy becomes the same, but realize that at an instant when the rate of change of energy is the same in both, then across 1, let me call it 1, if Q1 is the charge on 1, then Q1 by C into I would be the rate at which energy is dissipated in 1. And suppose at that instant the charge on this is Q2. Current will be the same, I, right? So then the rate at which energy is assimilated by the second one is Q2 by C into I. These two have to be equal. That is what we are seeking. That means Q1 equal to Q2. and that happens at t equal to RC by 2 log 2. That happens at t equal to RC by 2 log 2, when the rate of change of energy in both the capacitors will become the same. Do you realize that? No confusion? So passage 3 is about a simple parallel plate capacitor, and it's not an uncharged capacitor. There are two plates of the capacitor. One is given a charge Q1 and the other plate is uncharged, right? And then subsequently this key gets activated, right? And through a battery of EMF V volts, there would be charge exchange between these two plates. One, I want to find the charge flowing through the battery till the time steady state is reached, and charge on the two inner faces of the capacitor, right? This is the objective. Now, even before I activate this switch, what would be my charge distribution on the four surfaces? Q1 by 2, Q1 by 2 precisely, and Q1 by 2 on the two outer surfaces. This would be Q1 by 2 and minus Q1 by 2. Yes or no? This would be my initial charge distribution on the four surfaces before I enable this switch. How about it? Right? Now, once I activate this switch, eventually there would be an activity that will resume, which would enable exchange of charge between the two plates of the capacitor. That will take place till the time this V features entirely across the capacitor. Eventually, this terminal of the battery will arrive at the same potential as this plate, and this terminal will arrive at the same potential as this plate, right? And there would be no further exchange of flow of charge between this terminal and this plate, and this terminal and this plate. So what is my steady state here? Steady state is about potential V dropping across the plates of the capacitor. Potential V dropping across the plates of the capacitor. Yes or no? So once potential V drops across the plates of the capacitor of capacitance C, then the charges on the two inner faces would be CV and minus CV. Yes or no? This would be my final charge distribution on the two inner faces. Do you want to contest that or inquire? That is what it's going to be, right? That means now this had charge minus Q by 2, and now this has charge minus CV. Yes or no? Would you then not want to believe that the charge flowing through the battery must have been CV minus Q by 2, Q1 by 2, right? This minus Q1 by 2 will go down here along with additional CV that will make it minus CV. Yes or no? That must be the charge flowing through the battery. What do you say? And this CV minus Q1 by 2 will get added to Q1 by 2 to give me CV. So what's the charge flowing through the battery? CV minus Q1 by 2. What's the final charge on the inner surface of this? CV and minus CV. What's the work done by the battery? What's the work done by the battery? Huh? What's the work done by the battery? CV minus Q1 by 2 into V. That's the work done by the battery. Is it positive work or negative work done? Okay, assuming this is positive, then that charge, positive charge, is flowing from lower to higher potential. If it's flowing from lower to higher potential, that means charge is getting energized. That means work done by the battery is positive, right? So work done by the battery is going to be V into CV minus Q1 by 2. That's the work done by the battery. If the initial charge on this plate, see, charges on the two outer surfaces will never get tampered with. Even if you connect a battery, it's only redistribution of charge on the two inner faces. So this then will not get reorganized, right? If the initial charge on this is minus Q by 2, and if the final charge is minus CV by 2, What's the loss in charge? Loss in charge would be initial charge minus final charge. That, right? It's a loss in charge that is flowing out of the inner surface. So that's a loss in initial charge minus final charge. Minus q by 2 minus CV. That's a loss of from this inner surface. Is there any other part to this problem? So the next problem is about a capacitor, capacitance C, charged to a potential difference V volts. Charged to a potential difference V volts. So then plus CV will appear on the inner surface of this, minus CV will appear on the inner surface of the second plate. This is how it's going to happen, right? Now, so the battery is then disconnected, so that there cannot be charge exchange between the two plates. If the battery remains connected, then potential difference will be preserved. If the battery is disabled, disconnected, then the charge on the two plates put together will remain the same. On individual plates will remain the same. That is how it's going to happen, right? So in this case, if the battery is hurled out, then the total amount of charge on this plate will be Q plus CV. The total charge on this plate will be, on this full plate, inner plus outer surface, would be minus CV, right? Okay. Now, once I have done this, so the charge on this plate is Q plus CV. The charge on this plate is minus CV. So charge on the two outer surfaces is going to be Q plus CV minus CV by 2. Q1 plus Q2 by 2, isn't it? Q plus CV minus CV by 2. That means Q by 2 on this and Q by 2 on this. Yes or no? This would be the charge on the two outer surfaces, isn't it? Right now? Does it make sense? On the two outer surfaces, this would be the charge Q1 plus Q2 by 2. Q1 is Q plus CV, Q2 is minus CV. So Q1 plus Q2 by 2 is simply Q by 2. Q by 2, Q by 2 on the two outer surfaces. Now, if this be the case, now the total charge on this plate and this plate must be Q by 2, Q plus CV. So what would be the charge on, final charge on this? What would be the final charge on this? Q by 2 plus CV would be the final charge on this. Yes or no? Because the total charge on this plate must have been Q plus CV, of which Q by 2 appears here. So the balance Q by 2 plus CV will appear here. Yes or no? Evidently then, what would be the charge on this? Minus of Q by 2 plus CV would be the charge on this. The total charge on this plate plus this plate must be Q by 2 minus CV. Yes or no? Clear? So, what charge is, so final charge distribution is Q by 2 plus CV on this surface and Q minus of Q by 2 plus CV on this inner surface. And what determines the potential difference between the two plates? The charge on the inner surface divided by the capacitance. That's going to give me the potential difference. So what's the potential difference? V difference is going to be this charge on the inner surfaces, Q by 2 plus CV, and divided by C. So that's going to be Q by 2C plus V. Q by 2C plus V is going to be the potential difference between the two plates. Why is it that only the charge on the inner surface is instrumental? Because it's only this charge that's producing an electric field here. This Q by 2 and Q by 2 is producing zero electric field here. So this Q by 2 and Q by 2 will produce no potential drop in this region. So the potential drop is produced only by charges on the two inner surfaces. Yes or no? Got me? Right, so fairly simple. These are three capacitors connected as shown, a part of a bigger network, and A, B, D are at potentials VA, VB and VT. We want to be able to find the potential of O. We want to be able to find the potential at O. Now, so suppose O is at potential V0, right? So what will be the charge on this? C1 into V0 minus VA, drop is V0 minus VA from here to here, right? So the charge on this would be C1 into V0 minus VA, And the charge on this would be minus of C1 into V naught minus VA. Yes or no? Right? Similarly, what would be the charge on this? See, this is V naught, drop from here to here is V naught minus VB. So the charge on this is going to be C2 into V naught minus VB. And the charge on this would be negative of this. Right? The drop from here to here is V naught minus VD. What's the charge on this? C2, this is C3, right? This is C3, huh? This is C3, C3. So this is C2 into V naught minus VD. That's the charge on this. What's the charge on this? Minus of C2 into V naught minus VD, right? And the system was electrically neutral. Now realize that this plate and this plate are talking to each other. They are electrically isolated. Yes or no? See, all the three plates are talking to each other via the junction O. They can mutually exchange charge, and therefore they are a separate entity. And the algebraic sum of the charges on these three plates must be 0. Yes or no? The algebraic sum of the charges on these three plates must be 0. So this charge plus this charge plus this charge must be 0. So we have like C1 into V naught minus VA plus C2 into C3 into V naught minus VB plus C2 into V naught minus VD. That must be 0. And I can solve for V naught. Yes or no? So there is a capacitor that is charged by a battery of EMF V volts. And there is a dielectric constant K between the plates of the capacitor. Now if it's charged using a battery of V volts, the charge on the two plates is going to be CV and minus CV, Q and minus Q, right? Now this is pulled out, and it's brought to this state. It's made an air capacitor. Now in the process, the work done to pull this out, to bring the state, is given to be 4U, and we need to be able to find the dielectric constant of this. This is what we need to do, right? Where U is the initial energy of the system. Initial energy of the system is half of CV squared. One moment. U is half CV squared, right? Now, if the capacitance of this is C, what would be the capacitance of this? C by K. Right? And you know, while this is pulled out, the battery is disabled. Battery is disconnected. So if you disconnect the battery, what remains the same? Charge will remain the same, because charge will not have a way to fly out of it, right? So charge remains the same, right? Charge remains Q CV and minus CV, right? Now, the final potential energy of the system would be Q squared by 2C. This is the new C, right? So the new potential energy U prime is going to be Q squared, which is CV squared by 2 C by K. Yes or no? And so which is like half of K CV squared, as you can see. And the difference in energy must be the work done. So U prime minus U must be 4U. That's given. What is U prime minus U? So that's half of CV squared into K minus 1. That's equal to 4 into U, which is half CV squared. U is half CV squared. So half CV squared will get cancelled. K then is 5. K is 5. I'm assuming you got the same answer. Did you know? No. Okay. But I hope all of you understood what I did here. Right now? So there is a capacitor here, charge plus sigma and minus sigma, right? And there are two dielectric plates, K1 equal to 2 and K2 equal to 6. I want to find the ratio of potential drop V1 across this dielectric to potential drop V2 across this dielectric, right? Now, what would be the electric field in this region? Sigma by K1 epsilon naught would be the electric field in this region, right? What would be the electric field in this region? The electric field in this region is going to be sigma by K2 epsilon naught, right? What's the potential drop across this? This into D. What's the potential drop V2 across this? This into 2D. So V1 by V2 drop across this is sigma by K1 epsilon naught into D divided by sigma by K2 epsilon naught into 2D. So which is like a K2 by 2K1. How much is K2? Just 6 divided by 4, that is 3 by 2. Right? You know, we've discussed this situation. These are two concentric spheres, radii A and B. This is a case where outer is earthed and inner is charged. This is the case where inner is earthed and outer is charged. And we want to find the ratio of their capacitance C1 to C2. Very clearly, if you recall, you know, if the outer one is earthed, what's the capacitor? It's only between A and B, which is like 4 pi epsilon naught AB by B minus A, right? Yes or no? Recall this? We had a detailed discussion on this. And when this is earthed, then there is electric field here as well as outside. And this capacitor and this capacitor would be in parallel. Yes or no? Recall one day I had a discussion on this. So C2 is going to be, for this region, the capacitance is 4 pi epsilon naught AB by B minus A. Right, plus 4 pi epsilon naught B. Right? This to infinity would be 4 pi epsilon naught B. Have discussed this now? And now all that you need to do is find C1 by C2, whatever it turns out to be. 4 pi epsilon naught will get cancelled and so on and so forth. Right? What does it turn out to be? A by B? Okay. A by B. So we have a system of capacitors like this, and we need to find the charge on the plates of which capacitor? 2C? C? Okay. Now, evidently, suppose the charge here is Q, charge here would be minus Q. These are electrically isolated and neutral, so this must be net charge 0, so plus Q, and this will be minus Q. Right? And do you realize this actually is a closed loop only? Because this is also zero potential, this is also zero potential. So you can also join them and look upon this circuit as a closed circuit, isn't it? You know, effectively. So now I can apply KVL to the loop. I can apply KVL to the loop. Very good. So from here to here there is increase, so minus 10 volts. And then from here to here there is a drop, so plus Q by 2C. Q by C, 0. C is given to be 6 microfarad. And you can solve for Q. You can solve for Q. Yes or no? So there is a capacitor and the separation between the plates is D initially. It's then connected to a battery of EMF epsilon. Obviously, you know, there is going to be force of attraction between the two plates. There is going to be force of attraction between the two plates, and the charge on the plates of the capacitor, let's say Qn minus Q, right? Where what is Q? Q is going to be C epsilon. C epsilon, right? All steady state. What is C? C is going to be epsilon naught A divided by 0.8 D into epsilon, right? Epsilon naught A divided by 0.8 D is going to be the capacitance, right? Now, What's the force of attraction between the two plates? The force of attraction is this Q is known, Q squared by 2 epsilon naught A. Remember this result? That's the force of attraction between the two plates, right? And that must be, so when the plates will come closer together. From D it will become 0.8 D, right? So that means if they come together, there would be elongation in the spring. There will be elongation, and the spring force then would be K into 0.2 D. Would be the elongation in the spring, yes or no? K into 0.2 D would be the elongation in the spring, and this force of attraction between the plates would be balanced by the spring force to maintain equilibrium plate, isn't it? Force of attraction between the plates F must be balanced by the spring force Fs to maintain equilibrium of this plate finally. So that must be equal to K into 0.2 D, where K is the spring constant. Plug in Q equal to this and solve for K, the force constant of the spring. Oh, I haven't discussed this result. Why? I'll quickly tell you. See, this is, suppose this is the standby. Right. Originally, there was a 1 microfarad capacitor here and charged 200 volts. So then 100 microcoulombs minus 100 microcoulombs would have deposited on the inner surface of the two plates. Yes or no? है ना? 100 and now there is a capacitor 2C which is connected to this plate, and this plate of capacitor 2C is earthed. Question is, what would then be the final charge distribution on the two capacitors? What would be the final charge distribution on the two capacitors? No calculations required. Just no calculations required. Look at it very conceptually. Look at it very conceptually. Now, first of all, when I join these two, right, there should have been a charge exchange, right? Some part is normally, under normal circumstances, is liable to flow between these two plates to eventually equalize their potentials, right? But then, to manage that flow of charge between these two plates, a commensurate fresh charge must deposit on this plate. Suppose there was 20 microcoulombs that flowed into this, so this became minus 80, and this should have become 80. But how will this become 80? It's a free plate. It has no way to receive charge from anywhere else. So these two plates will then mutually decide that we don't want to put our friend in difficulty, because if I now have minus 80, where on earth will it give away 20 coulombs and acquire 80 microcoulombs? It cannot, right? There can be no prospect of change of charge on this plate, because how will it get any charge? This is a free plate. It's not joined to any electrical system, right? So this will maintain 100 microcoulombs, and this charge minus 100 microcoulombs will remain married to this 100 microcoulombs on the two inner surfaces. So these 100 and minus 100 are like bound charges. They remain glued to each other, right? Now if that means now if this is minus 100 and these two don't exchange charge, why on earth will Mother Earth oblige to give any charge to this plate? It would have, suppose there was 80 microcoulombs here, then Mother Earth would have said, all right, I'll give you minus 80, so that obviously, you know, if this is 80, this should have been minus 80, so that in the meet of the plates, the electric field is 0. So then if this doesn't have charge, already the meet of this conductor and the meet of this conductor are at 0 electric field. Why on earth will Mother Earth unnecessarily push charge onto this plate and cause a non-zero electric field in the meet of the conductor? You know what I'm saying? So Mother Earth will remain passive, inactive. It has no business to allow migration of charge to this plate, because this plate had remained passive.
Why did this remain passive in terms of exchange of charge? Because this minus 100 microcoulombs is bounded to this 100 microcoulombs, right? This cannot change, so this cannot change, and why on earth should any charge deposit on this? So this will remain 0 microcoulombs, and this will remain 100 microcoulombs. This will remain the final charges on the two capacitors. Sounds all right?